into the part where we understand what kind of ion for the counter ion that should be inside the resin and how is the selectivity as compared to the sample. Okay, in ion exchange chromatography, the lower the selectivity of the counter ion in the resin, it is easier being replaced by who? It is easier being replaced by the sample counter ion. Remember, we want the counter ion, which is the analyte, to be inside the resin, exchanged with its own counter ion. So that's why resin is usually functionalized with a counter ion that is lower than the sample itself. Okay, let us see on the table on the counter ion that usually functionalize on the. So for cationic exchange resin, okay, the most common counter ion is the H plus. Okay, why is H plus? Because it's among the smallest selectivity as compared to everything else. Means that the going down here to the table, barium is the most highly selective in the table. Means that if you have your counter ion attached to a barium, your sample would not be selectively replacing the counter ion. But if you just put H plus, if you buy a column with H plus as the counter ion, that's good because it's the smallest number. Okay, so if you have copper if you have copper as the sample, copper having selectivity of 5.3 can easily replace H plus because the number is relatively large. In contrast, for anionic exchange resin, it is functionalized with OH minus because the number is smaller. Sometimes you can also see anionic exchange resin has been functionalized with Cl minus, but it's 22 lah. It's very large. Means that Cl minus is only applicable to this kind of sample. See how big the numbers are as compared to the Cl. Okay, so if you have a resin with Cl minus, it is only applicable to this one. Okay, but if you have a OH minus, you can use for everything. Okay, because of the difference in the selectivity value. Okay, this is ion exchange chromatography apparatus high performance version. Okay, so that's why in the beginning I said to you, sometimes you can call IEC. Okay, sometimes you can call IC. Okay, because this is the same mechanism being used. If you see from here, it's the same. You have pump, okay, to pressurize the mobile phase to cut the electrostatic reaction inside this column of reaction. You have your buffer and also your organic solvent. You can add them, and also you have the detector as well as this one. But there's one thing that is different as compared to HPLC, GC, and so on. We have a compressor column, okay, or we call it as suppressor. Suppressor or compressor. Why? Because it can suppress or compress the high conductivity of salt. Sometimes you have to use a very high conductive buffer to get the electrostatic cut off from the analyte and the stationary phase. There's no other way that you cannot prevent the usage of this kind of buffer. Therefore, this suppressor column is there to enable you to detect the peak better. Okay, to enable you to detect the peak better. If you don't have the suppressor column, your peak might show up like this. Why is it very smaller than this one? Because, okay, the baseline has been dominated by the highly conductive buffer, okay, because it has been suppressed, okay, by the highly conductive buffer. So the peak want to be detected, but in the same time the baseline also want to be detected. So we have to get rid of this baseline by reducing the ion conductivity, okay. So because of this issue, because of the presence of this high concentration electrolyte that can suppress all those signal, and also because of the high sample ion conductivity swarmed by the background signal, okay, we can use ion suppressor column for both anionic exchanger and cationic exchanger. The trick is we use a column, okay, in contrast with the charge of the analytical column. That means if you are using cationic exchanger, okay, cationic exchanger column for analytical column, so you have to use anionic exchanger column for the suppressor, the other way around. Why? We will see the reaction later. Okay, so this is what I said just now, opposite to ion separation column. Okay, now for example, okay, the column itself is capable of neutralizing the exchanging element ions. This is the culprit now, kan? This is the culprit. Culprit means that it suppress the detector signal. Okay. In the same time, your suppressor column don't change the sample ion that much. Okay. For example, if you have been using a cationic exchange chromatography, okay, for cationic sample, and you don't have any choice but use hydrochloric acid as the element, you don't have any choice, and you know that hydrochloric acid is highly conductive because it's a strong acid, so you have to use a suppressor column in the opposite charge to the analytical column, which is the anionic exchanger, okay, hydroxyl ion over here. So let us see, when eluent pass through the column, the Cl minus ion exchange with the OH ion from the suppressor column. Therefore, it will form water molecules. So when you have water, the baseline will be lower as compared to higher baseline just now. Okay, so let us see the reaction. So in suppressor column, we have need an anion exchanger suppressor column, because it is functionalized with OH minus. It will trap it will exchange the OH minus with the Cl minus. Therefore, the resin will have the Cl minus, and OH and H will produce H2O. Problem solved. So, this resin will trap the Cl that is very highly conductive, leaving behind water for the detector to see. Okay, detector only see H2O. Detector will no longer see HCl. Okay, this is the extension of this explanation. Okay, for example, your sample is potassium nitrate and also calcium sulfate. Your analyte is cation. Why do I know it's cation? Because we are using cation exchanger. Okay, so you are analyzing K plus and also calcium 2 plus. Okay, so K plus and also calcium 2 plus, and you don't have any choice but use HCl as the eluent because of the selectivity. So you go into the analytical column, it will be exchanged with H plus, therefore your analytical column will have KCl, your analyte will have KCl and calcium chloride. Okay, while your this is after elution. This is after elution. So we have this culprit over here for after the separation, which is very highly conductive. Therefore, you use anion suppressor column that will produce KOH and calcium hydroxide. So where is the Cl? So the Cl is already exchanged on the resin, means that it's already on the resin itself, not in the buffer. The other way around with anionic exchanger chromatography. So you want the same sample from just now, but now you want the nitrate and also the sulfate. Okay, so you use a strong base anionic exchanger, which is functionalized with the CO3 2-. Okay, and you have to use sodium carbonate as the eluent. You don't have any choice, and you know that sodium carbonate is a very highly conductive buffer. Okay, and after you electrostatic, and then after elution through the electrostatic cutting and all, so you have the sodium nitrate and the sodium sulfate, which is attached to your analyte, but you still have the disodium carbonate over here, which is very highly conductive. So you use cation suppressor column to exchange with the H+. So leaving behind, okay, nitric acid, sulfuric acid, and also carbonic acid. So, and then we have water to neutralize the solution, therefore giving the low conductivity. So this is example of cation exchange chromatography. This is specifically for positively charged analyte. Okay. Can you spot what is the contradiction to oppose to what I said to you before during my introductory class? Okay, is that this is the only chromatography, okay, only chromatography, okay, that is using ethical column that can be separating inorganic analyte. Have you noticed it? Okay, these are all inorganic analytes. Therefore, ion exchange chromatography is the only chromatography method that can do inorganic separation, okay, on top of the organic analytes. Means that it can do both lah, as long as it is charged. That is the rule of thumb. If you see over here, 10 cations can be separated less than 11 minutes, and they are all having good efficiency and good peak height. The higher the peak means that the higher the concentration in the sample, and then the resolution are all good, okay, including this one. So if you see from here what kind of a column has been used, it is using Dionex ion pack. Dionex is a leading brand for ion exchange. Okay, in fact, it is the only brand that is used worldwide, because it's really established already. And the eluent, okay, what is MSA? Find out what is MSA. Okay, and it is using isocratic, the same with HPLC. Okay, and then they use any compressor column? Let us see. I don't think so. But they use suppressed conductivity. Conductivity is a type of detection and also has the suppressing ability towards the background mobile phase. Auto suppression over here. Or means that they have a column, sorry. They have the column because they have the auto suppression in recycle mode. So this is the example of anionic exchange chromatography. These are all anions, okay, separated less than 18 minutes. But if you see from here, the peak width is not that small, quite wide lah, okay. So these are all good. So what kind of this is column brand Shodex, you can find out in the internet. And also the detector is conductivity. Okay, so from now you see already that the detector used in ion chromatography is biologic conductivity detector, because it can detect any conductive analytes. So application of ion chromatography, of course, for deionization of water, determination of total salt, and also separation of metal ions. So this is the most applicable method for electroplating companies. So electroplating industries usually use IC. So when you work in electroplating industry later, maybe Uyemura, and then you have, I don't know what other companies are. So you can see IC in their labs. And also if you are analyzing food and beverage, you can see they use IC for determining the total salt in the food. And also the deionization of water. This is used ion exchange chromatography in the type of big column has been used largely by power plant industry. Okay, for example, last time when I work in Kappa Energy Venture, power plant situated in Kappa Klang, we have like several ion exchange chromatography column. The size is as big as, I don't know, few people, whereby we put resin inside here to neutralize seawater. We neutralize seawater to produce water to generate electricity through turbine. So if you are working in power plant next time, you will see this kind of ion exchange column, big size of industry to neutralize the salt. So as for deionization of water, in DI water, we have catex resin and annex resin. Why do we have these two? Because contaminants from the water is both positive and negative. So if you only have catex, you will only eliminate positively charged, such as microbes. While if you have annex only, you will only eliminate the salt. Okay, leaving behind the microbes. So that's why we have both in DNS water system. So this is how the reaction looks like. The impurities is copper nitrate, copper positive, nitrate negative. So catex, okay, will eliminate copper, and an exchange will eliminate the nitrate, leaving behind only pure water. Okay, so we have a deionized water system in almost every lab in Jabatan Kimia. You can have a look if you want to, or you can go into Millipore website. Okay, this Millipore website this is the brand that sell the ionized water system, and you can read the anionic and cationic exchange in the system. It is not chromatography per se for detection, but it is more to purification. So you have to remember that IC is used for separation and purification, just like the column chromatography that we learn in classic chromatography. Another example of ion exchange chromatography is we want to reduce or eliminate interfering ions. Okay, usually this is in electroplating lah. Okay, you can read on your own. Okay, so that's the end of ion exchange chromatography and ion chromatography. So please wrap up what you learned in the WhatsApp chat.